Hi, I'm Michelle Brosseau, a physics teacher, and in this video we're exploring electric circuits. We're going to go through an effective teaching sequence, addressing common misconceptions, and coming up with some analogies that will really help to boost your students' learning. This video is focused on students that are in middle school all the way up to high school and the teachers that support them. In this tutorial, we will be using the Investigating Electrical Circuits kit, which comes with this great magnetic whiteboard mat, which allows the circuit components to stay in place. For quantitative measurements, we will also be using the miniature digital ammeters and voltmeters, as well as the battery eliminator. Let's start with the simplest possible circuit that students could build: one battery and one light bulb. For students, the key idea here is that current only flows when there is a complete loop. I like to use a car analogy here. The charges are cars, the battery is home, and bulbs are toll booths. The cars will only leave home if they can get back. As each charge passes through a bulb, it pays a toll. That's where energy is transferred and useful work happens. Charge leaves the battery, travels through the bulb, and returns to the battery. If students break the loop, the charges can't return to the battery and the current stops. When students add a second bulb in series, this is a great moment to talk about energy transfer. With two bulbs, students can see that each charge now pays two tolls before returning to the battery, so each bulb receives less energy. For bulbs, they often have to try adding another battery. This is where battery orientation really matters. The batteries must be aligned positive to negative so that their voltages add together. When students orient batteries correctly, each charge gains more energy before reaching the bulbs and returning to the battery. In our car analogy, this allows each bulb or toll booth to receive more energy and appear brighter. When students add a switch, it's important they understand what the switch actually does. It's not there to add or remove energy. It simply opens or closes the loop. When the switch is open, students can see that the charges can't complete the loop and they can't return to the battery, so current stops. In our analogy, the cars won't leave home if they can't get back home. Students often think that the switch has to be placed in a specific spot to work. Moving the switch to a different part of the circuit shows that this isn't true. As long as the circuit forms a complete loop, current flows. What matters is whether the charges can complete the loop and return to the battery. In our car analogy, can the cars get back home? If not, then they won't leave. In larger series circuits, students can start to generalize patterns. In a series circuit, the same current flows everywhere because there is only one path for the charges to flow. Each bulb still acts like a toll booth, sharing the available energy before the charges return to the battery. Using multiple light bulbs provides a powerful observation for students. With 3 bulbs in series, the energy from the batteries is divided among all 3, so each bulb is dimmer. As students remove bulbs, the remaining bulbs receive more energy per charge and become brighter. With just one bulb, all of the energy is transferred at a single location before the charge is returned to the battery, and this one shines the brightest. Some yellow paper and some tape can do wonders to teach your students the differences between series and parallel circuits. The tape will be used to mark wires on the floor that charges can travel upon, and the charges will collect electrical energy from the battery, which has a fixed supply. The battery provides that electrical energy to the charges, which take it to the loads, in this case the lamps, which then turn it into heat and light energy. From there, the charges return to the battery to collect more energy until the electrical energy runs out. Let's see this one in action. A human model of a circuit is a powerful way for students to experience how circuits work rather than just seeing them on paper. In this model, students act as charges moving through a circuit, transferring energy from the battery to the light bulbs. The battery begins with a limited supply of energy, represented by energy tickets. The battery distributes energy tickets to the charges, and the charges carry that energy through the wires, which are represented by tape on the floor. As the charges move through the circuit, they deliver energy to the light bulbs. The light bulbs convert the electrical energy into other forms, heat and light, or for your older students, you can say thermal and radiant energy. In this series circuit, each charge takes 3 units of energy from the battery and delivers 1 unit of energy to each bulb as it passes through. After several trips through the circuit, the battery's energy supply is used up and the circuit can no longer transfer energy. This model helps students see that energy is transferred, not used up by the charges themselves. The charges keep moving through the circuit. It's the battery's energy that eventually runs out. Here are some diagrams of series circuits that your students can build at this stage of the unit. Now let's take a look at parallel circuits. This can be more challenging for students to build, but drawing it out first really helps them visualize where the paths split and then reconnect. A simple parallel circuit can be made using 1 battery, 2 bulbs, and a switch. In this kit, the connector posts are very useful. They act as junction points, making it easier for students to see where the circuit branches and then comes back together. Using the car analogy, 2 cars leave home together, modeling 2 charges leaving the battery at the same time, each carrying energy for the tolls. When the cars reach a junction, they split onto 2 different highways. Each car travels through its own path, pays a toll at the bulb, and then returns to the battery. This models how charges take different routes in a parallel circuit, transfer energy at the bulbs, and then recombine before returning to the battery. In a parallel circuit, each branch receives the full energy from the battery. We'll see in our human circuit model that parallel circuits can provide more energy to each bulb, but they also cause the battery to run out of energy faster than when powering the same bulbs in series. We can use the same human circuit model to explore what happens in a parallel circuit. The setup looks a little different, but the key ideas about energy transfer stay the same. Just like before, the battery begins with a limited supply of energy, represented by energy tickets. The battery distributes energy tickets to the charges, and the charges carry that energy through the wires, marked on the floor with tape. In a parallel circuit, the charges now have multiple paths they can take. Some charges travel down one branch while others travel down a different branch, each delivering energy to a light bulb. Each bulb still acts as a place where energy is transferred, converting the electrical energy into light and heat, or for your older students, radiant and thermal energy. Because each bulb receives the full energy per charge, the bulbs appear brighter than they did in the series circuit. The important difference here is what happens to the battery. Since energy is being transferred at multiple bulbs at the same time, the battery's total energy supply is used up more quickly. In this model, each charge makes fewer trips through the circuit before the battery runs out of energy. Students can connect this to what they observe in real circuits. Parallel circuits produce brighter bulbs, but the battery dies faster. This activity helps students see that brightness and battery life are both linked to how quickly energy is transferred from the battery, not how fast individual charges move. Just like the series model, this activity can be adjusted by changing the number of bulbs, the number of charges, or the amount of energy each charge carries, making it flexible for different class sizes and grade levels. Here are some circuit diagrams of parallel circuits that your students can build at this stage of the unit. Here is a very common student mistake. Students will add an extra wire in parallel with no bulb at all. This creates a short circuit, a path with almost no resistance. In our car model, it's like adding a brand new highway with no toll booths. A lot of cars rush through that path, not because they're choosing it, but because there's nothing slowing them down. This allows a very large current to flow, which can drain the battery, heat wires, or damage the equipment. We want charges to return to the battery after paying a toll at the loads, because that's where the useful work happens in the circuit. To measure current in a circuit, we use an ammeter. An ammeter measures how much charge flows past a point in the circuit each second. Because current flows through a circuit, an ammeter must always be placed in series so that all of the charge flows through the ammeter. In a series circuit, there is only one path for the charges to flow. When students place an ammeter in different locations in a series circuit, they observe that the current reading stays the same no matter where the ammeter is placed. This helps students build the rule that current is the same everywhere in a series circuit. Now let's look at current in a parallel circuit. Here, students build a parallel circuit with an ammeter in each branch to measure the current through each bulb, and another ammeter placed after the junction where the paths recombine. The first bulb reads 205 milliamps, the second reads 204 milliamps. When the students measure the current after the junction point, the ammeter reads 409 milliamps. Using a magnetic whiteboard mat allows the students to write these values directly onto the circuit diagram as they collect data. This helps the students organize their observations and focus on identifying patterns. From this data, students can build an important rule about current in parallel circuits. The total current in the circuit is equal to the sum of the currents in each branch. In this example, students use 3 ammeters so they can see all the measurements at once. The same investigation can also be done by moving a single ammeter to different locations in the circuit. What matters most is giving students the opportunities to compare readings and reason about what they mean. To measure voltage in a circuit, we use a voltmeter. A voltmeter measures the electric potential difference, which tells us how much energy each charge gains or loses as it moves through a component. For example, a charge will gain energy as it moves through the battery, and a charge will lose energy as it moves through the light bulb. For younger students, voltage can be thought of as the push that drives charges through the circuit. Because voltage is a comparison between 2 points, a voltmeter must be placed in parallel with the component being measured, with one wire before and one wire after that component. Let's start with the voltmeter across each light bulb to measure how the voltage is shared. Here, the first light bulb has a voltage of 0.6 volts, and the second has a voltage of 0.7 volts. When students measure the voltage across the battery, they read a total of 1.3 volts. This is where the whiteboard mat is extremely useful. From this, students can build the rule that in a series circuit, the energy gained from the battery is shared, not necessarily equally, among the loads. Now let's compare this to a parallel circuit. Again, have your students draw the circuit first, then place the voltmeters across each bulb. In a parallel circuit, each branch receives the full voltage of the battery. This means that each bulb gets the same amount of energy per charge, even though the current may be different in each branch. Each bulb here reads 1.2 volts, and when the students measure the voltage across the battery, it also reads 1.2 volts. Writing these values onto the whiteboard mat really helps students immediately notice the contrast with the series circuit. Comparing voltage measurements in series and parallel circuits helps students build strong rules that they can apply when analyzing more complex circuits. For this activity, we're going to be adding in Arbor Scientific's Battery Eliminator. This tool is so useful for changing voltage on the fly, which is great for Ohm's Law explorations. Once students understand current and voltage separately, they're ready to explore Ohm's Law. Ohm's Law describes the relationship between voltage, current, and resistance, and it helps students predict how a circuit will behave. To test whether a component obeys Ohm's Law, students build a simple series circuit with a switch, one bulb, and an ammeter. Using a variable power supply like Arbor Scientific's Battery Eliminator, this allows students to quickly change the voltage while keeping the circuit the same. Students start at a low voltage, like 1.5 volts, and gradually increase it. It's important not to increase the voltage too much because the light bulbs can overheat and burn out by the ammeter. These values are written directly onto the whiteboard mat or into a data table so students can clearly see how current changes as voltage increases. Students then graph current versus voltage. If the graph forms a straight line, the component is considered ohmic, meaning the resistance stays constant and obeys Ohm's Law. Now, most light bulbs do not produce a straight line graph. As the filament heats up, its resistance increases, causing the graph to curve. This shows students that many real-world components do not behave as ideal resistors. Students can repeat this investigation using different components, such as resistors or small motors. Comparing graphs helps students see that Ohm's law is a model and that different components follow it to different degrees. As you're teaching circuits, your students may come across some of these common misconceptions. The first is when drawing parallel circuits. Some students may add an additional wire with no load on that branch. Evidence from doing this is by having them trace each path on their circuit. Can an electron leave the battery and travel through each path while paying a toll? The first one's okay. The second one's okay. But why would the electrons travel down those paths when they have this last path that they can travel through for free? That short circuit will allow the electrons to pass through too easily and can cause the circuit to overheat. Asking students which light bulbs light up in circuits with switches can bring forth some more misconceptions. For example, students may think that as long as the electrons can reach the light bulb, that they'll light the light bulbs up. So they may trace a path something like this, but we need to remind them that there needs to be a continuous path between both terminals of the battery through the light bulb in order for that light bulb to turn on. So instead, they may try to reason that the electricity can return back to the battery this way. Well, in order to address this, we can show the students that they're telling us that the electrons are both moving this direction and this direction in the same stretch of wire. So that tends to address that misconception. Providing students a visual of a circuit that can have light bulbs that are both on and off can help with this misconception. For example, we have a continuous path here, which will cause this light bulb to light up, and we have another continuous path that will allow this light bulb to light up. But due to this open switch, there's no continuous path for that final light bulb to light. This really helps students understand when switches can cause light bulbs to be on or off. Speaking of visuals, they really are a game changer in helping our students understand circuits conceptually before we start bringing in any mathematics. These energy tickets, converting electrical energy into heat and light, our circuit diagrams, the circuits that we build in class, those give students multiple avenues to understand these circuits concepts before we bring in any calculations. This final tip and visual will leave the senior physics teachers singing your praises. In the lower grades, we tend to talk about voltage as the pressure or the push on the electrons driving them through the circuit. By the senior grades, we want students understanding that voltage is the energy per unit of charge. So here we have our charge, our car, and here we have a delivery of energy. And when we have a circuit with low energy per unit of charge, a lower voltage, that charge will leave the battery, deliver that energy, and then head back to the battery for some more. If we change the circuit to one with a higher voltage, we still have our charge, but now it's delivering more electricity, more energy. So here's our charge. It's going to go through and deliver a bigger bundle of energy before it heads back to the battery. This is a great way to show that voltage is energy that each charge is carrying and helps to support the work that we were doing with our energy tickets in our human circuit. Thank you very much for watching this video. I hope you and your students enjoy building circuits. All of the great teaching tools you've seen here can be found at Arbor Scientific.